Okay, I guess we could start. Hello and welcome to today's webinar on control, HVAC design in the 21st century. Today's webinar we're broadcasting from EQUA Simulation headquarters here in Stockholm, Sweden. It's a very nice sunny day. I hope it's the same in where you guys are at. There's a lot of diverse audience in today's webinar. I think we're expecting somewhere around 133, 140 participants. My name, the guy's talking, is Mark Azar. I'm today's host. And joining me today is Per Carling from EQUA Solutions. Today's webinar is going to be a little bit different for those of you who logged in and got to attend the previous webinars. It's going to be a little bit different in a couple of ways. The first of which is today's webinar is 90 minutes. So it's a little bit long. It's a sort of a podcast / online test or course, crash course in control. And it'll be in a podcast format. So we're going to have a little discussion between us, Per and me. But more on that a little bit later on. For those who don't know us, Mark Azar, I'm the guy on the upper right corner right there. You can see my picture. I'm the guy who looks like he's meditating, trying to figure out where his life went wrong or remembering how to smile. It's not a very nice photo of me, but... And on the lower right corner, there you have Per Carling. Per, I think you have the same excited look as you had first day of kindergarten. So we were saying that today's webinar is going to be 90 minutes long. The first, it's going also to be divided into two parts. The first part is a 30-minute PowerPoint presentation where Per and I are going to go through some topics, discuss some topics on control and HVAC modeling. And then we'll try to rush through those topics, through those discussion points to go to the meat of the webinar, the main event, which is demo cases. For the next 60 minutes, we will present 4 demo cases that we have prepared for you guys. We think they're really, really interesting, and we hope you will find them useful and interesting as well. We will also be featuring a couple of polls. We will throw at you a couple of polls to get some feedback. We do appreciate you just taking 1 minute to answer these polls, and if you do have any question all throughout this presentation, there will be a Q&A session at the end. We'll try to dedicate 10 to 15 minutes for Q&A. So if you think of any question and you just want to note it down, go ahead and write it in the questions pane. You see that dashboard on the GoToMeeting. And you'll also get the opportunity to raise your hand, and if you want to verbalize, if you want to give us some feedback, we'd appreciate it at the end of the session in the Q&A as well. For those who can't attend for the full 90-minute session, we will be sending out a link to those who registered. If you do follow that link, it'll get you to a recorded video of this broadcast, so you won't be missing much. However, we would like you to, of course, stay with us till the end. So we have, I don't know, shall we go through the material?
Yeah.
Shall we start?
Sure.
Okay, a little bit background on us. So my name is Mark Azar again. Hello, everyone. I've been working with EQUA since 2013. I work mainly in the field of control automation. My background is in mechanical engineering. And previously I worked as a CFD consultant, as well as a lecturer and researcher at KTH, the Royal Technical University in Stockholm, in the Building Services and Energy Technology Division. Per, would you like to introduce yourself?
Hello everyone, my name is Per Carling. I'm CEO and co-founder of EQUA Solutions here in Sweden. We are mainly working with training and support of IDIs. But also on consultancy in building projects, both for simulation and monitoring. and I've been with EQUA since 2011, and I've been using ICE for quite some time. Yeah.
Yep. It's good to have you with me, actually. I'm not used to this webinar format. I'm used to lecturing with students. I can see the reaction. So you here sitting next to me, well, it's going to make it more fun and less lonely. Okay, so let's get right to it. Today's topics, as I said, this webinar will be divided into two sections: a podcast topic, which is a PowerPoint presentation, and the demonstration cases. And the topics that we're going to go through is, first of all, we're going to try and answer or make the case for control. Why do we need to bother with control? And we'll try to answer this in a general manner. We know the audience has a diverse background. Some of you are architects, some of you are academic people, some of you are consultants. So we'll try to touch base on all of that. Then we're going to talk a little bit about how control is changing the way we do design today in HVAC. After which Per will present a very interesting case study to showcase how control affects building in practice.
Yeah.
I think you have something very interesting aligned for us today. Yeah. And I'll then come back to make the case of why use eye-to-eyes when you want to model control, and give you guys a little sneak preview on what we're working here, exciting new features that will be up and coming concerning control. For the demo cases, we gave this a little bit of thought, and we wanted to present 4 basic cases. The first of which is a shading control, how to implement a more realistic shading control. And in each of these cases, we will be using the version handling platform to showcase several cases, different modes of these cases as well. We'll go through tips and tricks. We'll go through good common sense strategies in control. So I'm sure there will be something useful for everyone. After the shading control case, we will show a dew point cooling control case, and in this one we're basically trying to avoid condensation when you have cooling panels or chilled beams inside as room units. How to control your chiller or your district cooling in order to avoid that and save energy. Another case we're going to show afterwards is the mixed ventilation control, and this is also an interesting case where for special rooms like an atrium, one would have both opening of windows and a mechanical ventilation together in the same case, and we want to show how to create a control structure so you don't have overlapping heating and cooling at the same time, as well as maximize on free cooling. So that's a very interesting case. Finally, we're going to touch base on something that we feel is a little bit underappreciated in the industry today, and that's night setback and optimal starting. So we're going to talk a little bit about typical night setback control strategy, and we're going to show a little bit controversial, I think it will be a little bit controversial control that I set up for optimal starting, predictive controller. So that's what we have aligned for you in today's webinar. If you just walked in and saw these topics and those are not for you, now's your chance to walk out. That's your exit cue right there. Or else we could just go through and dive in. So I won't linger on too much on why control is important. I think it is. I know it is. I believe it's a black and white issue. But what I wanted to point out here is that eye-to-eyes can be used in many, many ways. Based on how I used to use eye-to-eyes before coming here to EQUA as a consultant, I used to use eye-to-eyes basically to size equipment, to find the maximum and the minimum heating, cooling demand, and basically find worst-case scenarios. And that's a very interesting use. It's a use that I think many of the people logged in right now do, whether it's in certifications, whether it's in HVAC design. And also as a CFD consultant, we used to use IDA to get good initial starting values in order to speed up the simulation of a CFD process. So, but I never did control. I never looked into the advanced level. I never went to the schematic. It didn't bother me that much. However, IDA ICE is very much a dynamic simulation tool. It took a lot of effort to try and simulate realistically how to get from point A to point B, from the initial starting point to the peaks. And if we only look at the peak performance, then we're missing out all this path dependency, how to get there. I think we're only seeing a little bit of the picture and missing out on the bigger image here. So I believe that IDA ICE could help us understand how systems behave by seeing how they change, how behave under different loads, basically, in part loads. We already know that buildings don't operate at full load all the time. Barely 1% of the full year operation will be at full time. So seeing how systems behave under changing load is important. It also allows us to evaluate the performance and efficiency of complicated systems in an easy and fast way. So here I'm saying easy and fast because I'm comparing with the classic approach of, I don't know how classically you would evaluate, for instance, complex systems, but for me, using IDA ICE is a pretty easy way to evaluate these structures. It also gives us a realistic outcome, a much more realistic outcome when we're taking the interaction between these different systems, when you're considering the interaction between the demand and the supply side, between the building and the zones and the air handling unit and the plant, your chiller. It should also help you simplify your design. It simplifies your design by getting rid of oversized systems, unnecessary controls, which you might inherently, without knowing, just designing. And it should speed up their design process. A lot of people, I think this is a little bit controversial because a lot of people think that IDA ICE complicates sometimes the design process. Yeah. Using dynamic tool is an effort that people don't want to invest in. But it's there to simplify and speed your design, to help you evaluate these multiple scenarios, complex scenarios in parallel, to get a sound decision in the end, where otherwise without the dynamic simulation tool you wouldn't be able to. And all this is basically works because controls are there. So controls for me is like the oil in an engine. It makes everything works flawlessly, beautifully, very well. And a lot of people don't look into that, but we're going to shed light on this issue in today's webinar and see how sometimes control can make an engine fail and what to do about it. So if we take a look on how does control affect our simulation or our modeling HVAC design, and we compare it with the classic HVAC design approach. Well, with a classic HVAC approach, one would size using rules of thumb typically. So all transient features, internal gains, solar loads, everything is designed using specific rules of thumbs and specifications. In modern, using dynamic simulation tool, you would do that based on the dynamics, the physical dynamics of how things are changing. You would select your systems based on a fixed COP instead of an actual COP that you could measure. You would configure your system based on out-of-the-box staging method, for instance, instead of relying on the existing control structure. And basically you would lose a lot in terms of capital and running costs if you don't use the modern CFD, because using the modern simulation tools should help you correctly size your systems, lowering your capital, speeding up this design process in whole. So you should typically end up with a faster simulation time, not this lower simulation time, if you focus on control, a more stable design. And that, in the end, basically, for instance, I would use IDA ICE as as a learning tool for me. These lessons learned is really hard to get a grasp of design when you're doing classic steady state or static calculations. You never know how the systems are going to interact, and if your design is going to work until it's too late, right? Mm-hmm. So here to talk about until it's too late, Per Carling, Per, you will present a case?
Yeah, I'll present this case study, and the message is, or I would like to reinforce what Mark talked about, that control is so important, and we will discuss this office building that you can see on the picture. It's the Hagaporten office outside Stockholm. It's the headquarters for the consultancy company ÅF. And in this building we started trending all the data in the energy management and control systems even before the occupants went into the tenants went into the buildings. So we've been logging it thoroughly for almost or over 8 years now, and it's been logging of all the HVAC signals, around 300 signals, I think, with a 5-minute resolutions for over 8 years. So we have a good grip of what's going on in this building, and we have been doing a lot of tuning. So and we learned that control is so important to reduce energy use. I should mention also in this project that we formed a working group that met on a regular basis, and all the decisions when it came to this tuning work were taken within this working group, and we didn't allow the operators of this building to interfere, or actually they were part of the group, but they weren't allowed to take their initiatives on their own, but everything had to go through this working group. So we had a good structure of this work. Yeah, I can turn to the next picture maybe. So the major reason for this tuning work in this building was that the simulated energy use was quite close to the requirement. It was a green building certified building, and the energy use or the requirement according to the certification system was around 82 kilowatt hours per square meter a year, and also the simulated value was around that order of magnitude. So we didn't have much margin built into this project. So therefore we wanted to be sure that we could keep track of the building and also try to tune it below this requirement. In this diagram you can see the wide bars represent the facility energy. So this also corresponds to the measure you use in the Swedish national code. The thin bars represent the energy used by the tenants, so it's basically the tenant electricity and the cooling for servers. We call it process cooling. The first bar, or the bar left to the left, is the simulated energy. Now it's almost 10 years old, this simulation model, so I won't be too proud of it. IDIS has developed a lot over these 10 years, and also we've learned a lot. So you could do a better model than that. Still, we have an approximate level, I think, which is reasonable, but a lot of things to improve there. The first early prediction we did based on short-term data was about 100 kilowatt hours per square meter a year. Maybe you should note also that all these years are normalized, weather normalized in the same way, so they are really comparable. Also, as you understand, we have good grip or control of how the building was used and if we had any problems and so on. So maybe I can note that in year 2010 we had some problems in the building due to a broken heat exchanger, for example. What we did was, after this early prediction, we did a number of tuning measure or took a number of tuning measures. We changed the set points for the cooling beams. We also changed the schedule for the cooling pump distributing the cold water in the building. And we also implemented night setback on the room heating system. And as you can see there, we managed to decrease the energy use by approximately 20 kilowatts hours per square meter a year. Now, I only count the facility energy because that's what's included in this requirement to green building. Then we have incrementally tuned the control system down to around 65 kilowatts hours per square meter a year at year 2014. Actually, in 2015 and 2016, the energy use was slightly increased, so I skipped that because it looks nicer. At least I'm honest. So we didn't really do any sophisticated things. We just looked at data, tried to think, and then changed the settings of the control systems.
So the only things that were changed were schedules and set points.
Nothing. So there's no refurbishment or changing any components or anything like that. Just control settings. And so I think the message is quite clear here, and that is that we could save like more than 30% of energy just by tuning the control system, basically. Maybe we should mention here also that we didn't touch the fan operation schedule. Otherwise, that's a very easy way to save energy, but that was fixed over the years. So. Yeah, maybe you can change the next one. Yeah, and Mark, you will soon show some nice examples, and one of them is on night setback. What you can do in eighties. In this building, we introduced night setback in a very simple manner. We just changed the set point of the supply hot water temperature to the room heaters by 10 degrees between 5 in the afternoon and 5 in the morning. So here are some carpet plots showing the district heating, the set point of supply hot water temperature, and the control signal to the heating valve. And what you see here is on the y-axis is the time of the day, and on the x-axis is the time of the year, and then we color code the variable. Actually, you don't see the scale very good, I think, but it doesn't matter. You can see the pattern there, and that's enough. So the first month, January, we didn't have any setback, and then you can see, for example, that the set point of the supply hot water temperature is varying slightly, and that's because it's a function of the outdoor air temperature, as is common. But then I think in the end of January or in the beginning of February, we introduced this setback, and so between 5 in the afternoon and 5 in the morning, we decreased the supply hot water temperature set point by 10 degrees Celsius. And if you look at the district heating, you can see there's, if you look carefully, you can see there's a decrease during night, and also there's a peak in the morning at 5 o'clock, and that is, of course, when you start to reheat the building. So we of course selected that time schedule carefully, so the peak there didn't coincide with the peak that you get when the air handling unit starts.
Right. Yeah. Do you also have penalties on these peaks?
Yeah, there's penalty on the energy supplier. Yeah.
Actually, it's quite uncommon to have a good set of data like this. I'm seeing no data missing.
Yeah, sure. It's I mean, I picked the year with the best, with the common, well,
to work with.
Yeah, sure. We have other years or other periods where we miss some data, but it's I think many energy management and control system can have this opportunity nowadays, and it's a good way to learn how the building is working, to log and look at this data. We can also analyze a little bit the control signal to the heating valve. Basically, it's showing the same pattern, but it's a little bit clear there that the control signal decreases a little bit when we introduce the night setback, and then we have this peak in the morning. So we'll see if Mark can come up with something smarter later on this webinar, but I'm sure he can. Anyway, we approximately saved around 7 kilowatt hours per square meter a year.
So we have a question thrown at us. So space cooling in the simulation is double the actual consumption.
Yeah.
For that?
I think the interpretation here is that the model is 10 years old.
Oh.
And I'm not proud of it, so let's leave it there. On the final slide on this case study, I must take the opportunity to say that it's useful to have a model to compare with when you evaluate measurements. I mean, how do you else know what to expect? I think also a model is a good tool for making what-if studies during the commissioning phase.
Oh.
But for this to be meaningful, I think it's important to have the model that is detailed enough, also modeling the control in detail.
Yeah. Okay, thank you, Per. Before I make the case for why eighties, why use eighties for control, modeling control, I would like to throw a poll in this moment, just to see in what way do you guys use eighties. So please take a minute just to answer this, and it'll give us an idea of how to steer our conversation in the demo cases.
Yeah.
Okay. So let me share some results here, maybe. So 29% of you say they use it mainly for certification. Because this is expected, right, Per? You guys also do a lot of certification.
Yeah, we use it for lead and Miljöbyggnad. Yeah.
Right. 58, more than half of you use it for mainly heating, cooling load calculations. We have 9% of non-first-time users or haven't used IDA before. So maybe here just to see what it is capable of. 27% say mainly for academic purposes, a lot from academia. We do get that a lot. And a healthy 38% for HVAC design, sizing, evaluating, and control structures. So I think it's a good mix.
Yeah. Would be interesting to know how different between countries, but maybe we can analyze that later.
Yeah. Okay, so let's get back to...
I think we have a question there about air handling unit ventilation in swimming halls. I guess the general answer is that anything is possible to model in eighties, but we also have a separate tool for that, ice rink and pool. So there's a certain tool for that takes care of the, for example, the wet surface in the pool. So it's possible to simulate, but need some care.
So let me see if I can get back the my screen there.
Yep.
There we go. So we all know that eighties has a lot of interesting features that make it stand out from other dynamic simulation tools. The first of which is this variable time-stepping solver, which we are very proud of. Basically, eighties' solver automatically detects and automatically shortens the step in order to capture accurately the dynamics of the system. So while other solvers or other tools might have a fixed, discrete time step that the user usually has to define, and so it does calculations at certain specific fixed time intervals at these points, for instance, and miss out on a lot of these peaks, a lot of these dynamics. eighties automatically shortens the time step in order to capture all the behavior of the system. And this is very powerful. A lot of users know this already. But what does it mean for us for control modeling? It means that basically one is able to model continuous controllers without worrying about the time stepping, without worrying about if the controller in real life will actually behave quite well physically, whether the system will oscillate or not, because this solver is like a workhorse. It will keep on shortening its time step until it finds a good solution for you. Now this is a double-edged sword, the way I see it, because then IDA-ICE is so lenient and flexible that it will try to solve any control system, any control structure and strategy you throw at it, irregardless of whether it makes sense or not. And as a penalty, often people get slow running times, slow simulations, numerical instabilities, numerical errors, and they would be complaining. So we will see basically in the demo cases how to approach this carefully. But this is one strength that IDA-ICE has. Another one that you know is that in IDA-ICE we compile all the models together. We solve at every time step the full problem. We don't simulate and co-simulate each of the parts and then stitch these signals, these solutions together. And this is important for us in control as well, because you could have control signals in between these systems, in between the building body to the air handling unit to the plant. They need to be communicating with each other. So if you simulate each one separately, independently, and stitch them together, you are prone for error propagation. If you have one error in one system, that will lead to an error in all of the system. So this is something that IDA-ICE avoids. Another thing is that, and which is really important in control, is that all these models are open. You are able to view all the models and log any variable you like. And this is one of the main philosophy of control, basically, is being able to put the sensor as close as possible to the variable you would like to control. We're going to see in the demo cases that the farther away the sensor is, the more dynamics you neglect, the harder it is to get a good control that gives you the correct set points. So in IDA-ICE there is no restriction. You are able to log any variable you like. However, what few people know is that in IDA-ICE you have an inherent hierarchical structure of control. So IDA-ICE basically has levels of control. It has a building level control. We call it a supervisory level control. It has zone level control. It has unit level control. And so these building level, zone level, and unit levels are able to communicate together, able to send signals. So you could send signal from the zone to the plant, then take a action signal back, a control signal back from the plant to the zone. You're able to communicate all throughout these levels in the background in a very easy way. And we're going to see how this helps not only design better control systems, better control strategies, but also enables much faster simulation time. Because you reduce redundancy, you reduce the need to model several controllers in every zone when you have one controller communicating to all zones. So these are the things we will highlight in the demo cases. I think a sneak peek before we delve into the demo cases, what we are working on. We are invested in this line following control. So we're working on using programming logic control, PLC, what we call PLC language, directly in IDA-ICE. So you'll be able to take a PLC code that a control engineer would typically write and understand, and you would be able to integrate it. So if you don't know much about control, you're able to communicate with your control engineer, and he's able to share with you his control strategies, and you'll be able to test it within the IDA-ICE environment. And that's quite important and an interesting feature that it will be upcoming. Something else we're working on, I'm excited about and quite involved in, is the real-time state tracking. And this is basically using the IDA-ICE energy model in the operation phase. When you have a good energy model and you have good data, sensor data from the building, how to fuse those together in order to track and see what is actually happening in real time from your IDA-ICE model. And the third topic we're working on concerning controllers is modeling discrete controllers. And this is, again, throws us back to the question that how do we model more realistic controllers, and helps us to communicate with control engineers. So basically all this effort that we're putting in right now is aiming to bridging the gap in control design and using this one tool, IDA-ICE, from concept to design to operation phase. And that's something we believe in, this path. But so enough talk.
Yeah.
We're ready for demos. I don't see any more questions out there, so let's demo away. Okay, I think there's a lag in the screen there. So as I said, all throughout these demos, we'll be using the version handling system. It's this platform in IDA-ICE that allows me to manage and compare different cases all at once together. So that's a useful tool for me. I use every time to do, if I want to compare cases, if I want to do a parametric study, I usually rely on that. And in the first, maybe I could increase this like that, maybe it's better. So in the first demo case, we said we're going to talk about shading control. In this case, we're going to present 4 modeling cases comparing shading interior control. So that's basically when you have your shades being controlled by daylight sensor inside the room, to shading with exterior control, when you have a more realistic scenario where you're controlling your shades from an exterior sensor located at the building body, building facade. Mm-hmm. And then with the interior control, we have 2 child cases there that are related to it, where we're going to see different versions of the same control strategy, just different improved versions, how to improve the simulation time. So I'll open the first case, shading control, interior. And basically all throughout these demo cases, we'll use this building, office building, 2-floor office building that I think some of you might be familiar with.
Quite familiar.
Quite familiar, yeah. It's an IFC model that comes shipped in basically out of the box with IDA-ICE. So the idea here behind this is that the most typical user of IDA-ICE, when he wants to simulate shading control, he would basically open the room unit, insert some shading, and in the draw control panel would select one of the default cases there. So he would either control it using sun, schedule, or a mixture, sun and schedule. And he also has the option to create a custom control there. But for me, this is quite an optimistic point of view when you do this for every window, because your main assumption, principal assumption then, is that you have a sensor on every window measuring this sun radiation on that window. And that is not in real life cases.
No, I don't think so.
No. Usually you would have, what, 1 sensor to control?
I guess it depends on the size of the building. I've seen several weather stations, but maybe, yeah, differs a little bit.
So we thought in this case we will show how to use 1 sensor to control multiple windows. And in this case I'm going to use the sensor located, the daylight sensor located inside this Office 7 room to control all the orange shades, while using the sensor located in the atrium, in this zone, to control the shades that, the blue shades, the atrium shades. So just here, first of all, to do a little demonstration, but by what I mean shading control. So in the end, you'll be able to see something like this. The orange shades going down, the blue shades going down. The blue shades, they have slat angle on them. So the slat angle on the blue shades will go between 0 and 90 degrees, as well as being drawn down and up. So there's two control signals there, while the orange shades only have up and down function. So we have 2 functionalities there. So how do we do this? Well, the approach here is to introduce you guys, or the main idea here is to introduce you guys to this function here called supervisory control, and that's the building level function. That will basically create a controller that is located on the building level and is able to communicate to the plant, to the air handling unit, and to all the zones using one signal. And the way to do this here, the way we implemented this, is going to the panel here that you see on the left-hand side and going to links. In the links on the left-hand side, you'll be able to see signal sources and control targets. And this basically gives you all the modules that you can get signals from and all the targets that you can send signals to. So in this case, I'm using zone sensor, this little guy here. And what this zone sensor does basically is it exports all the signals from the zone to wherever I put this zone sensor. So here I'm connecting this zone sensor to the lobby. I can connect it to any zone I like or any group of zones by name, by location, floor level, zones that are connected to the air handling unit, zones that are connected to a certain body part, or all zones. For this sensor, I'm connecting it to the lobby, which is my atrium. And from it, I have an option here to select a list of signals to export from this zone. I'm selecting daylight, and it's measured in lux. So that's the sensor inside the atrium. If I have a list of zones here, I have also the option to apply a function on those, either to take the minimum of it or the maximum of these signals, or an average, some variation of average. So in this case, from the lobby, I'm taking daylight, and it doesn't matter what really I put in apply function because it's only one zone. So that zone signal here is coming to a proportional controller, one for the shading and one for the slat angle. So this one will give me an output between 0 and 90 degrees, and this one should give me an output between 0 and 1, 0 being undrawn and 1 being drawn. And I'm sending this signal to the zone, and I'm calling this target, my zone target, atrium, building to zone control atrium. So if I opened this, I'll see that my controllers are connected, one to shading and the other one to slat angle. And I'm replicating this. I'm doing the exact same thing for my office. So this zone sensor over here is connected now to office. It's number 7. That's the one located on the far left corner. I'm also taking the daylight signal, and I'm giving it to a proportional controller. And since the offices, they don't have a slat angle, so I'm using just one controller there to control both. And I'm calling this building to zone control office. And also one good practice here is whenever you're creating a control macro, I always put an output file. The output file you could find in the utility section. The output file will allow me to log all the variables and see how my control structure is behaving. This is very, very good when you're debugging and seeing what went wrong in your system. So that's all I have to do in the supervisory control, basically. It's just measuring the daylight sensor inside the room, one in the atrium and one in the office. So how do I send this signal now to the zones or the windows that I would like to control? Well, there's many ways. The first way I would like to show is sending it directly to the windows. And here you can see that I created, for every window, if you double click the window, you could create a control macro, as we showed here. You can have a new custom control. I created 2, one called shading control macro atrium and the other shading control office. Let's open one of those and see what's inside. There's no control structure inside. It's just an import module. This module here imports the signal from the central building, from the supervisory control to my unit, basically. So if I double click this, I see that shading and slat angle that I created, those interfaces in the supervisory control in the building level. And I'm directly linking them to my actuators, to the shading signals and control slat signals of the window. And I have the same one for the atrium as well. It's just an import signal, but this one is importing from building to zone control atrium, the one. So I do this for all of the orange ones. I connect them to the sensor that is located on building on Office 7, and the blue ones for the one for the atrium. So in essence, what I have is one supervisory control connected directly to multiple windows. That is the first base case that I built.
Okay, so Samer has a question. You see that? Can you decide the location of the sensor in the room?
Yes. Well, if you go to system parameters, what you could do here is you see side on, where is that? Here, method of measurement of daylight level. And so when we went to the zone sensor and we selected daylight signal, this is actually measured at first occupant. So it's an average over floor area or point measurement at first occupant. Since it is at first occupant as a point measurement, wherever you move your occupant, that measurement will move. So if I open any one of these zones, for instance, the entrance, you can see here there's an occupant. I'll double select the floor and you can see where the point occupant is. You can move this around. However, if in the system parameters you select average over floor, then that's affixed over the floor area. Good question, Samer. Thank you. Okay, so that is my base case. What about the other child cases? What I did was I kept everything the same. We're still working with the same model here, with the same window model, but I changed one thing. In the supervisory control, for this proportional controller, when you open it, you have a couple of parameters here. I don't know if you guys have done this before, but it allows you basically to set the maximum and minimum of the signal that you would like to control. So basically when I'm saying I want to control my daylight to be within 2000 and 2100 lux, that's basically what's being translated here between high and low. So the proportional controller would try its best to keep the signal, the incoming signal, between 2000 and 2100. And how does it do this? By outputting a signal between 0 and 1. That is my control signal. So that's basically what my controller is doing. And by default, this tau here, time constant on in signal, is 0. So in my child case and this second case, I changed this to 60. So the only difference between those two cases is this tau. What is this tau? And that is what I wanted to introduce in this base case. Basically, this tau is the time constant that you can put as a low-pass filter on the in signal. So when your in signal is noisy or changes, basically has a dramatic change in a very short amount of time, you can filter this signal before processing it, before giving it to the proportional controller. So in the base case, I'm not filtering my signal. In this case, I'm putting a 60-second time constant on the low-pass filter. And we're going to see what dramatic effect it has on the output. So I'm putting a 60-second tau on all these four, well, basically on 3 proportional controllers. That's the only difference between these two cases. And I'm calling this one control smoothed, because it's the input signal is smoothed or filtered. There's no noise in it. In the third child case, what I'm doing is I'm using the case where I have smooth control, where I'm putting filter on the in signal, but I'm changing the way I deliver my signal, my control signal, from the supervisory to the windows. So in this case, instead of sending a signal directly from the supervisory control macro to each and every window, I'm going to send the supervisory control signal to each zone, and then from each zone to each window. why does that matter? One would say. Well, some of these zones have multiple windows. This zone, for instance, office number 7, has 2 windows. If you send your signal supervisory control signal to each and every one control macro in these windows, that's two control macros per zone. Now, this for zones with 1 windows, that doesn't matter. But for an atrium, for instance, there are more than 10 windows there. So that's 10 macros, 10 calculations, redundant calculations that you have to do for this one simulation. So when you send the supervisory signal to a zone controller, you're sending it to the atrium, then that one signal is being spread to these 10 windows without replicating that control macro. And we will see how it affects the simulation time. Drastic effect. The last case here we have is exterior control. So what if we want to do a much more realistic type of shading where we actually have a sensor located outside the building? Well, I took the same case again, this case, and this time for the, here, it's the same case. And this time in the supervisory control, instead of the zone sensor, I put, because IDA allows me to access any of the models, and because IDA allows me to log any of the variables, I'm actually bringing the shading model and the window facade model and logging the radiation that is being cast by the sun, basically, diffuse and direct, onto that window. So this will give me a watts per meter squared of radiation. And I'm converting it multiplying it with the light efficiency or efficacy, daylight efficacy of 75. I'm converting it to lux. So from watt to meter squared to lux. And then I'm using the same controls, the same set points for these controls and filtered tau. So the only difference between this and the base case is that I moved my sensor from inside to behind the shades. This is actually outside, just behind the shades. And we'll see how it affects our output results. So with the version handling system, you have this option to update all and run all the simulations in parallel while you go sip some coffee, or you go home and come back the next day. And you can plot and compare these in a report or a table. What I decided here to compare, which is interesting, is what we're trying to control. The daylight at the desktop office, number 1, this is at first occupant, and in the atrium. So this was the control set points here were between 500 and 600 lux, and for the atrium it was between 2000 and 3000 lux. So if we plot this, we'll see, let's remove the exterior for a second here. We'll see that all cases, the shading, I'll zoom this for you guys to see better. We see that for all cases, the shading interior control, the one which is smoothed, and the one which is smooth but with sending the supervisory control to the zones instead of directly to the windows, all give the same output. They're all the same type of controller. So, you would ask me then, how did this filtering of the signal affect this? And all of them are successful, trying to limiting the daylight to 500 lux. Well, to see how these are different, quite different cases, let's open them and look at how much time it took to simulate them. We're simulating for 3 days. We're simulating from June 12th to 15th. And for the base case, it took me 68 seconds to simulate. So this is the case which doesn't have any filtering on the in signal. For the smooth case, which has a 60-second constant, it took 44 seconds. Now that's a big, for 3 days, a 20-second reduction. That's huge if you have a big case and with multiple windows. Now let's see how did the smooth control with the decentralized, sending the signal to the zones instead of the windows fared. Instead of going from 68 to 44, this is 25. So we went from 68 from the base to 25 seconds. That's a big, big difference. And that's very, very important. So we now see the effect of doing controls properly, of filtering out the in signal, of focusing, putting more effort on simplifying the structure, how these control signals propagate in the model and communicate with each other. What about the effect of changing the sensor from interior to exterior? Well, keeping the same controls, just changing the position of the sensor, location of the sensor, you can see that we failed in our output. We couldn't achieve the set point of 500 lux. We only achieved 200 lux. And this begs to differ here, that these shading control companies, they're installing a shading sensor outside the window, but they do not know what type of window we have. So when the sensor is outside the window and is measuring 2000 lux, inside, because of the glazing, properties of the glazing, you can have the solar transmitters to be as low as 60% coming in to the window. So you're trying to control the inlight while missing out on all this phenomena of light being refracted, reflected, and absorbed. And that fails. So where you position your sensor is very important as well, and something to look out for.
So we have a question. How do you get the windshade object into the supervisory macro? Can you show that?
Yes. So there's in here in the left panel, you have a couple of you can see here you have envelope, for instance. And here you can get the macros for that you use for radiation. And the one for shading is actually found under all. It's called, where is it?
Windshade maybe.
Yeah. It's called shade C. I have a lot of my own macros here, so zipping through. Oh, there you go, shade C. So if you drag that, you create this. And of course, this needs to be interfaced with a
face model.
Yes, here, wall faced exposed to radiation. So by dragging those, you're allowed. And if you double click this shade model, you'll be able to see what variables you can log here. And I was logging this I total out, the total beam and diffuse radiation after shade. So basically my sensor was located after the shades. I hope that answers this question. So I think this is all we have for the shading control, yeah. Unless there's more questions. It's possible.
There's another question. Can you please show how to give the signal to the zone and then split it up to the windows?
Yes, of course. So this is where I'm doing this. So I created the supervisory control macro here, and then I go to my lobby, this zone, the atrium, that. And instead of going to the window itself, I will go to this advanced tag here. And under advanced, you'll find zone controller. So I created two zone controllers, one called atrium and one called office. Let's open it. It's the same thing as you would have done for a window, basically. So this is getting the signal from the supervisory control to the zone. And then when I go to my window, when I select these windows, I suddenly get this option, central zone control. So if you put this central zone control, it gets its signal from the zone controller, which in turn gets its signal from the supervisory controller. So if you actually build this model, I think I have one built. I can show it maybe. No, that's not it. So this is the same case, but I have a schematic, so I already generated the mathematical model of the case. So you would see my building level supervisory control is located here. So if I double click it, you see this supervisory control that we created. And it is connected to all this, these zones. So you see the signals here, the lines where it's going to the lobby, for instance. And if I open my lobby, I can see it going to the windows here, the window control macro. So if I double click that, that's a window control macro. When you have a zone level controller, there'll be one macro here, and then only one macro connected to all windows, instead of having 1, 2, 3, 4, etc. macros. And that's what basically creates this dramatic effect in the simulation time, reduces simulation time a lot.
Yeah, we have another question. Why is the sensor located behind the shading? Is this realistic? Is it usually located on
That's
the
a good
facade?
question,
Yeah.
actually, yes.
The answer is yes, I guess.
Yes, you're totally correct. It's just the way I set it to the controls. I think you do have an option to take the radiation directly from the facade, but I just did that for no apparent reason. Good question. Okay, shall we move on to dew point control? So again, I'll maximize this. So what did we want to see in the dew point control? We wanted to visualize the effect the dew point control has on two things. The first is avoiding moisture and condensation. So when you have cooling panels inside and you have high humidity inside, you don't want to supply a low set point for your chiller to these cooling panels, or else you'll have condensation and it'll be a rainforest inside, right? That's not good for us. But we also I wanted to show two things. The first is that it actually reduces energy when you have a realistic chiller model. And that's where we're going to veer off, I think, a little bit and talk a little bit about fixed COP versus partial load curves. So here we have a dew point control, and I'll open the base case here. And again, we're going to use the same model. We're going to use the same model all throughout this demonstration, that little office building that we have. And now for the dew point control, one way to do this is to take a representative amount of humidity that is located inside the building, and based on that, shift the temperature of the set point for cooling for the zones, right? So our typical user would, for instance, open the air handling unit, and he would put a temperature or humidity sensor on the return air side. So this sensor here you will find in the air handling unit panel here. If you drag this all the way to the down to the lower, you find this state sensor. And if you drag it and double click it, this sensor allows you to basically log several things, 10 options. You can log mass flow, temperature, CO2, relative humidity. So in this scenario, my interest is logging absolute humidity ratio. So kilograms of water per kilogram of dry air. And I put it on the return air side because the return air is the most representative of what's happening inside the building. Now I would like typically to export this signal, whatever the sensor is reading, I want to export it to the supervisory level or directly to the plant where I have my chiller. So in this case I'm exporting it to the supervisory control just because I can and I want to demo it. And I do this by going to the links section here and using this reference to remote link. This is basically an export. What it's doing, it's exporting the signal from the sensor to the supervisory. And if you look here, I named it humidity on return. If you open this, you'll get a tree structure like you would see in an outline in eye-to-eyes. And I navigated towards HVAC components, went to air handling unit, my state sensor that I employed, the variables that is being logged, and the output signal of that. And I said, okay. So right now this is basically acting as my humidity ratio sensor. What am I doing with this sensor? I'm feeding it to a linear segmenter. And basically what we want to do here, our control strategy is staying 1 degree, right, above the dew point temperature. So on the x-axis, it's not really clear here, but on the x-axis you'll be able to see the humidity ratio, and on the y-axis is the set point that I would like. And I did it in a way so that the minimum set point we have is 15. We don't want to go below that. And we go always 1 degree above dew point as the humidity ratio goes up. And then I'm exporting this signal to my plant. And this little to plant export, you can find it in links under this targets. So my target here is from building to plant control. And as always, I have an output file to log. So if I open my plant, I see this little import from building to plant control output. If I double click it, I see that I'm here, the dew point set point is what I want to get from this. And I'm feeding it to my chiller, to the set point that dictates the temperature of the cold water going to the zones. This channel here is going to the air handling unit, and these pipes here are going to the zone.
Maybe you should mention that you have replaced, I guess, the idle units with the water-based units.
Yes, I should mention that. So two things I did from my base model. The first is I turned off the cooling coil in the air handling unit because I want just to use the cooling panels to cool down my rooms, and I want to see the effect on COP, which will come later on. The second thing I did was all the room units, which by default are ideal coolers and ideal heaters, I replaced the ideal coolers all by chill beams, sized typical 500 watts, just by default. So now the cold water going to the zones, it's going to those. Now one additional thing I did was I went to my COP, and instead of putting here by default it comes in constant and having unlimited power, I actually want to study what effect does dew point temperature has on the performance of my chiller. So I went in and put a performance curve, and this standard chiller model uses a DOE2 chiller model, which requires that the user import reference coefficients for performance. Now, on your dashboard there, you would see in GoToMeetings, you see handouts, 1 out of 5 there. I don't know if you guys see that. I put an Excel sheet called chiller performance coefficients. This Excel sheet, I'll open this for you. You can download it and open it. My Excel is opening. There we go. And what it allows you here to do is basically say from no load to my chiller to 100% load. So that's the part load ratio here. What is the cooling capacity? So this is some data you would get from the manufacturer. And what is the electricity consumption of that chiller? And if you input this colored brownish, light brownish data cells, it automatically generates these coefficients A, B, and C. And you can input those in eighties directly. So you can go ahead and use this Excel to get a more realistic performance curve of the COP. And I changed the sizing of it. So I already know I did my cooling load calculation, and I know the capacity. So I put there 15,000 watts. So that's the only thing I changed there. So that's my base dew point temperature control. I'm keeping 1 degree above the dew point, and I have a realistic COP on my chiller. That's all I did. Then I have a case where there is no dew point control. It's just the chiller. So I have no supervisory control. And in my plant, I have my performance curve, but the zone supply temperature is fixed at 15 degrees, which is what comes default with IDIs. And then in my third case, I will show it later, maybe, because it's an improved case for the other two. So how does these two cases perform? To figure this out, I logged a couple of interesting variables here. I logged the water-based cooling power to the zones. This is basically what my chiller is requiring to deliver the cooling demand to the zones. The chiller supply temperature, and the COP and the part load ratio. So let's see first the chiller supply temperature to zones. I'm going to plot this, and I'm going to remove the case where we have improved control. So looking at this, maybe I'll zoom in there. You can see that the one without the dew point control is in green, and it keeps the supply temperature steady at 15. However, the one with dew point control, the first 2 days, I'm simulating 3 days, again in June from 12th to 15th. The first 2 days, it's keeping at 15. Probably the humidity ratio is pretty low. And then when the humidity ratio inside the building goes up, it's increasing 1 degree above that humidity ratio. So I see here is supply temperature increasing to 17.6 degrees. So my controller is working as expected. That's good news. How about the energy? Again, I'm going to remove this and zoom in. Well, you see when the dew point temperature is the same, they both consume the same amount of energy. But in the last 2 days, when the dew point temperature control kicks in, then it goes from without dew point at around 10,000 watts to with the dew point temperature control to around 9,000 watts. So that's 1,000 watt energy saving, just directly like that. So we're doing both energy saving and moisture control, condensation control. Interesting to see, something interesting to see here is the PLR. I'm going to again zoom in, and you're going to see that having a realistic coefficients on your performance curve, you see that your chiller rarely operates at full load. Here it's operating at 55% in the worst case in June 15th. Actually, I think less than 1% will operate at full load, and all the rest is below. So that explains the power consumption saving. So one issue arises from this dew point control, and I think you pointed this out to me the other day, is IDIs models the system's physics very realistically. So basically, when the air handling unit is off and you have a humidity sensor on the return, right? That humidity sensor is going to give wrong signals. It's going to be off. It's going to go berserk, basically, and give out signals. And the same thing happens in IDIs. In IDIs, when you turn off the ventilation signals, what happens is numerically, we turn down the mass flow to very small number, an epsilon, 10 to the minus 12. And then when that mass flow rate is 10 to the minus 12, that humidity ratio will go nuts on you, will give you false readings. So if I have, one way to avoid this type is, again, to the rescue, our zone sensor. So here, instead of, I'm still exporting to the plant my temperature control, dew point temperature control, but instead of having a linear segmenter taking its signal from the air handling unit sensor, I'm using my zone controller to log all the zones that are connected to the air handling unit. So I take all zones connected to air handling unit, and in this pop-up window, I choose dew point temperature. And I'm taking here an average over volume. Now, maybe this is not the best thing to take an average over volume. Maybe average over flow rate is a little bit more important, or some might want to take the minimum of the dew point and do a control on minimum. But I'm taking this signal, and then I'm adding 1, so I'm keeping 1 degree above that dew point temperature signal. And I'm making sure that I don't go below 15. So I'm using the maximum of that signal and whatever 15 is. So when this temperature dew point control goes below 15, my output here will be 15. So this is another way of doing dew point temperature control. And the plant, nothing changes in the plant, it's the same. But this ensures that since I'm not dependent on the mass flow rate and the humidity sensor, this is more stable. Although it's probably less realistic to have a humidity sensor for every zone. But from a simulation perspective, it's more stable.
Yeah. So we have a question. Was there an effect upon the room air temperature by adapting the dew point temperature? I guess the answer, maybe we can leave that for the listeners to try to do a model and check out.
Yes.
I'm sure there will be some effect, and I guess that's one of the drawbacks with this system, but better than starting to rain inside them.
Exactly. All these models, all these demo cases will be online, as well as this recording for this webinar. So you guys will have access to this, play around with this, develop your own better controls as well.
Yeah. We also have a couple of questions around model predictive control.
Too early.
Yeah, too early. Okay.
Okay, I guess that's what is the question there?
Have you ever considered the possibility to connect IDEs with, for example, MATLAB to enable simulation of more sophisticated controllers like model predictive control? And we also have one regarding future work on control in IDEs. Is it possible to use the PLC for performing model predictive control in IDEs? If not, are you working on a feature for including MPC in IDA?
Okay, I'm really happy to hear that. So there's a lot of interest. The answer is yes. We have a new API out, and this API allows you to connect any external software from Python to MATLAB to Modelica, anything connected to IDEs. And by connected means you're able to change a variable, log any signal, get any signal through this API. And we have Schneider Electric testing this, working on us on this API. So the answer is yes, and this has been done before, interfacing MATLAB. I interface MATLAB in real time. We have IDEs being used in hardware in the loop control as well. As for the PLC, right now, once it's implemented and we are able to import PLC language, ladder scale language to IDEs, then that would be possible as well. Okay. How are we on time?
8 minutes left.
We're going to let's go through. I guess it's gonna be more time. The third case is a hybrid ventilation case. So we have only two things to show here. The first I wanted to show is how to have both mechanical and leverage natural ventilation, what they call natural ventilation. We like to call non-mechanical ventilation. So how to leverage the free cooling from that without getting heat from the mechanical ventilation. And the second thing I would like to show is how to do branch control for valve system. So this is 2-in-1 demo case. So let's open our little office there. And here to see the effect of ventilation and opening windows, I just removed the shades to have solar load, full solar load coming in. So what basically I will be doing is I will be opening this upper window here and the lower window here to create this draft coming into the zone. And if I double click here, I'm controlling it through the zone control macro. So the zone control macro is opening those two windows. So let's see how it is controlling the opening of these windows. Well, okay, don't be afraid. That's the first thing I need to say always. We're basically using three conditions to open the window in this case, and we're combining these three conditions with a multiplier. So a multiplier, when you have binary input to it, is basically an AND operator. So unless this is 1, 1, 1, the output here will not be 1. If any one of those conditions is 0, we will have a 0. So that's what this multiplier does. So what are these conditions? The first condition is a schedule. I don't want to open it at night. I don't know, maybe someone will jump in. Or it's not useful for me when there's no occupants. So according to a schedule, which is office schedule between 8 and 4 o'clock, I'll get a signal of 1. And if it's not, it's a 0. What about that second option? The second option is I want to ask myself, is there potential? And the way I'm measuring if there is potential, I'm taking from ambient, this model here, ambient, I'm taking outside air, T air, and from the zone, I'm taking inside temperature from the zone, and I'm comparing them. I'm saying if the difference between inside and outside is larger than 2 degrees, then there is a lot of potential. If it is not, then there is no potential. So if I open this proportional controller and look at my parameters, basically I put my high upper limit at 2 and my lower limit at 0. This means if the difference is anything between 2 and above and infinity, I'm going to send a signal of 1. This means, wow, a lot of potential there. If it's 0 and below, I'm going to send 0, so no potential. My third condition is interlocking set points. So when I open a window, I want to make sure that my ventilation, mechanical ventilation, is not affected. So the first thing I would want to do is turn off my mechanical ventilation. But also the second thing I want to do is, what if it's not enough, the potential that is out there? There is 2 degree difference, but what if the wind speed, for instance, or the internal gains are too high? Then at some point I would want to close this and start the mechanical ventilation. So the way to decide this is I'm going to take the cooling set point from this set point module. I'm going to take my cooling set point that the mechanical ventilation has, and I'm going to say I'm going to leverage free cooling. I'm going to use free cooling until I reach 2 degrees below my set point. If I reach that 2 degree margin below my set point, then probably it's not enough to open the window. Then I'm going to turn it off and start my mechanical ventilation. Now, some might argue maybe 2 degrees is too much. We might want half a degree or 1 degree. But this deadband, this interlocking between the opening of windows is very, very important for control perspective, not to have overlapping set points. And the way I'm opening here is, in one case I'm using proportional controller, in the other I'm using a thermostat. And the thermostat basically acts as an on and off controller. It's going to give me a signal of 1 and 0. So that's how I'm opening my windows. Now, how am I controlling my ventilation? If I open the zone, the atrium, I'm using this system type. You can create your own custom control. I created one and called it hybrid control. If I open it, I also have 3 conditions there. The first one is a schedule, when I turn on the mechanical ventilation and off. The second one, I want to test if my window is open. And the way to do this is to take a signal from this zone module that says opening. And this basically tells me how many in meters squared do I have large vertical openings. So when my window opens, this number will spike. So I want to take this and test it. Is it open? And then convert it to a signal between 1 and 0. If it is open, then it's a 1. If it's not, then it's a 0. Or sorry, if it is open, it's a 0. I don't want mechanical ventilation. If it's not open, then it's 1. I want mechanical ventilation. And for the mechanical ventilation here, I'm choosing to control this ventilation using temperature. So I'm taking my cooling set point to the PI controller, and then I'm measuring the zone temperature here. And I'm making sure that it keeps between the set point of the cooling set point. Now, here you can use, of course, humidity, you can use pressure, you can use any type of control to send a signal to your ventilation. So in this combination between the mechanical ventilation and the natural ventilation, I'm able to avoid this overlapping system. The other thing I want to show in this model is using this supervisory control as a branch controller for the valve systems. So I'm going to use in the supervisory controller my zone sensor to log for several zones the CO2 level in ppm volume. And I'm going to take the average of that. Taking the average of the CO2, I'm going to send a signal to these zones. And using one signal, which averages the CO2 of several zones, I'm going to control the valve of all these zones. So if I open one of these zones, you can see here that instead of hybrid, I have ventilation macro. And opening the ventilation macro, I'm importing this signal from the supervisory control. So this is one way of doing valve branch control. The other case I would like to show is simply replacing one component, only one component in this model, and that is in the opening of the window, the zone controller. Instead of the on and off thermostat, I'm going to have a proportional controller. So that's all, and the difference between smooth and non-smooth. And let's check out the results. To compare these, did I save? I think so. Yeah. To compare these, I'm going to look at the temperature in the atrium for both cases, plotted. And look at here. It's very, very interesting. When you have, let's look at it by day. So what is happening here is that for the thermostat, is trying to open this window and cycling. This is a classic hunting effect in control. It's trying to open, but as soon as the window opens, the temperature drops and then it's trying to close it again. Whereas in the proportional controller is very, very smooth action here. So what do you think this would cost us in a simulation? This is, remember, this is just 2 windows and for 3-4 days. Let's see its cost on simulation time. With the one with the thermostat is 60 seconds. For 3 days. The one with a proportional controller, 24. Huge impact.
So maybe that's part of the answer for the next question we have. Are there any differences between using a PI controller, a proportional controller, and a thermostat?
Yes.
Yeah. Yeah. So
that's there you go. But there's also fundamental differences, but I think it respects its own webinar or course, just to look at all these control modules. But we're short on time, right? We
minus one.
Minus one. Okay. Last case. Night setback. For night setback, I wanted to show several cases. The first one doesn't have a night setback. Let's open that and start with that. So here we have a plant, and for the boiler, you have an option in IDICE by default to put a schedule, setback schedule. So you're trying to control the set point temperature based on outside temperature. So that's T-air2, that's outside temperature. And you have some linear controller here. If I open this, you'll see that, as outside temperature drops to -25, we want our set point to be 70, and then goes proportionally down to a minimum of 20. And then you have an option of putting a schedule. I'm going to create a case where I don't have anything, so always off, the first one. For the second case, I'm going to put a schedule, and a typical schedule would be to have setback during normal days between 4 o'clock and 5 o'clock. So 5 o'clock in the evening and 4 o'clock in the morning, I have a setback of 10 degrees. And then no setback throughout the day. And then I'm going to create my own predictive control, which is a little bit, it might be a little bit controversial, but I've been tinkering about this for a while now. And so instead of a schedule, I'm putting this macro controller. And opening this macro controller, there's 2 conditions on this predictive control. The first one is using the rate of change of the temperature inside the building. So I have a zone sensor here logged to all zones connected to the air handling unit, measuring the mean air temperature. And I'm getting the minimum out of this, the worst case zone. I'm filtering the in signal to smooth out for noise, and then I'm calculating the rate by using the derivative module. So this will give me how many degrees of change I have per second. And on the other hand, I'm using the zone sensor to get a signal called time before use. And this is a very special signal in IDICE. that we also, I think, developed with Schneider Electric. And time before use will basically output how many seconds do you have at any one moment before the next occupant arrives in the room. So from this level here, I'm taking the absolute values because when the occupant is inside the room, the values here are negative. And I'm multiplying with the rate of change. So basically, effectively, what gives me here the output of this control is, or the signal, is how many degrees of change up until the next occupant comes to the room. And here this is just an on-off controller. Instead of thermostat, I created my own on-off controller, which gives me -10 or 0. So if this value is less than or equal to 0, it's 0. It's -10. If it's greater than 0, it's 0. And then I do variations of this controller. Instead of on-off controller, I use a proportional controller. So I have the plant, I have this predictive macro, everything on the left-hand side is the same, I didn't change anything. On the right-hand side, instead of on-off controller, I'm using a proportional controller in heating mode, and I have a set point here, 0. And I'm going to do a parametric run on this between 0 degrees limit, 0.5 degrees to 2 degrees. So let's compare and see what happens. I logged the boiler supply temperature to the zones. And this is the last thing I want to show you guys. So when we have is a no setback, the one that is blinking there on the screen is the temperature supply to the zones. And it's always high, around 42 to 48. When we have a scheduled setback, it cuts down at night from 4 in the morning to 5. You can see it here dropping down by 10 degrees to 32. When you have an on-off controller, it cuts way, way earlier. It cuts way earlier. Let's see where does that cut. Now remember, the on-off controller doesn't have a schedule, so it's determining when to start and when to turn off. And we can see here that on one of the days, it's starting to ramp up at 7:30. On the next day, it starts to ramp up at 7:21. On the third day, it starts to ramp up at 7:23. It's starting to ramp down here at, let's see, at I think 2 o'clock. Yeah, around 2:15. So even before the occupants leave the room. Here it's ramping down at 3 o'clock, 3:30. So it's deciding by itself when to ramp down and have this 10-degree setback. And as we move up this proportional control, the more we move towards the no setback. The more, so it's basically a design decision because you're always going to compromise between how much energy you do want to save and how much thermal comfort, right, do you want to achieve. So let's see how much energy do we save. Wrong button. So this is the graph for energy, and what's interesting here is I'm going to show you in table form. So this is per day, and here when we don't have any setback, the mean, this is the mean value here, the mean value that we're seeing all throughout this 3 days from February 13 till February 15. The mean value here is 7,900 watts with no setback. Just by putting a schedule, we get 7,000. How about when we use the on-off controller? It drops down to 6,600. That's from 8,000 here to 6,600. That's more than 30%, 20% reduction. So as we go up between 0 degrees, 0.5 degrees, then of course, then we're going more and more towards the no setback, and we're compromising on thermal comfort as well. So how much are we compromising on thermal comfort? We can log the air handling unit, return temperature of the air handling unit, and see here that with the no setback, At 8 o'clock, we're reaching around 20.6, 20.8 degrees when the people start to come in at 8 o'clock in the morning. And when we have the predictive on and off control, it's 20.6, 20.5. So it's a 0.2 degree difference in mean air temperature. So maybe that's a okay compromise for us. That is something up to the designer to decide. But what I wanted to show is that night setback works. It's usually an underappreciated control strategy, and you can do nifty things. You can do these predictive controls quite easily in IDA. I think we're running out of time, so we better do the Q&A fast. Do you guys have any questions for us? I see a lot.
I think we answered most of them step by step.
If you guys also have some feedback for us, raise your hand, and we are really happy to hear from you. We're trying to read through the... Oh, we have some hands raised, maybe. Weather forecast for predictive control. Basically, what I do right now is a very hash way of doing this. I basically bring the PRN file of the weather and move it forward by day and then feed it to IDICE. Of course, that's not maybe the best way to do this, but it is one way of doing weather forecast predictive control. Of course, if you interface it with MATLAB or Python, then you're able to do this in a better way. We have hands raised. Maybe you could... yes. I'm going to give the microphone to Estevan. Dr. Estevan, do you have a question for us or some feedback?
Maybe you need to make sure that you have unmuted your microphone. Istvan Dr. Kistelegdi.
Yes, hello. Can you
Hello.
hear me?
Yes, we can hear you.
Hello, nice to hear you back. I have a question according to ventilation control.
Okay.
It is ventilation control according to the indoor relative humidity, especially in swimming pool, but also in other rooms, in industry halls or stuff. And we are trying to create a control for air handling unit as well as for windows, in according to be able to control the indoor appropriate indoor relative humidity level. So, for example, between 50 and 60%. And for this case, do you have any hint for us? We create some controls already, but maybe you have any hint for us to make it. Yeah, this is a pretty general question, I know, but
do you have? Are you facing any problem with the current control that you have, or because we have a motto? If it works, it's good.
Maybe you just can show in either the
we only have
humidity control.
Yes, we only have one. This is made with help of thermostats, and yeah, thermostats is on off with some dead bands. It's not that sophisticated, so I don't know if you have any hint how to go forward to make it better. Or
we have here on the screen this option, VAV system with humidity control. Do you think this will help you with because this by default it will create a proportional controller which controls the ventilation signal based on the set points that you have here, the relative humidity set points that you create in the zone. Does that answer your question?
This answers me a bit, yes.
Okay.
Yes. Now we have a very special topic what we work on. It's a swimming hole. So we have some humidity that is coming out from water. Then humidity from the occupants as well. Relative humidity indoors. And yes, this was our goal is to measure the humidity indoors and then to give an appropriate control to the air handling unit to change two things. Firstly, the cooling temperature to get dehumidification, so drying air, and secondly, the control of the air volume, how much airflow we want to change or increase or decrease. So this is in my head, in my imagination, how we should go on.
Yes, well, so with this VAV signal and humidity, you're able to control the ventilation signal as well as temperature in the zone. And in the zone, when you place an occupant, that automatically generates humidity. And you can also put a equipment that generates humidity as well, simulating
Actually, I think when it comes to swimming halls, it's quite a specific. We have a separate plug-in for that actually called Ice Pool and Rink, and which can handle the moisture.
We don't have it. We don't purchase it yet, but I know there is a possibility.
Okay, you know it's available. Yeah. But also, I think you should know it's possible to build anything really around the air handling unit, measuring the humidity.
So
whether you want to control the flow rate or the humidity in the supply air or in the return air. And on the screen you can see, for example, we have a default air handling unit called extra heating coil dehumidification. So there you have a start with a simple air handling unit, and then you can build a control around that cooling coil where you dehumidify the supply air, based maybe on the return air or something. So that's available. But I guess we done some swimming halls, and it seems like we end up in quite sophisticated simulation models with heat pumps and things like that, also taking energy from the wastewater and so on. So but maybe we can. I mean, we can always help you also on a consultancy basis if that's needed.
Yes.
Yeah.
Okay.
Yes.
Thank you, Dr.
Could you? Yes. Short question. Could you show this special or not special equipment that can even produce humidity in the zone?
Yes, definitely. I don't think it's anything special. It's just
the equipment.
The equipment. Yeah. You have here liquid water emission per unit.
Okay.
So how many kilograms per second? And that's, again, maybe that's not the latent load mechanism that you would get from a swimming pool, but you can...
We have some from the HVAC planner, from the HVAC engineer. We have some values, how much kilogram per hour or how much gram per hour is emitted by the water, so roughly how they dimension their equipment. So
okay.
Okay. Thank you so much, guys.
Thank you, Dr. Stefan. Thank you for your input. I'm reading some of those questions. I'm really sorry, Andreas, and for if I rushed through the last, we're short on time. But again, the webinar will be online, and you'll be able to go through, see it again.
Yeah, we have one.
Show some different from the boss.
Yeah, show some different air handling units. Well, I guess you can look for yourself in the palette. We have a number of air handling units predefined.
Here on the left hand side.
We're thinking of someone in particular. Maybe you can add that to your question.
For how long will be online? Well, until we answer all the questions, or you guys leave. I don't know.
Yeah.
What do we have again? Thank you guys for your positive feedback. I'm seeing a lot of nice, interesting messages there. Are there any references for the MATLAB API LARP? Yes, there are. Is it commercially? Well, it's free now. You can try it, and we have some documentation. We're working on it.
Maybe you can send a mail to the support.
Yes, if you send us a mail.
Yeah.
We'll send you a link. Is it possible to get explanation in German? We do have a German support team. I'm not sure if they will are up for translating our...
No, I don't know either. We have to discuss that.
Sorry.
Yeah.
Can I just launch some polls for you guys, just to get some feedback from you? Take a minute again to tell us. It'll help us really improve these webinars, and in the future if we did anything wrong. So how did you find this webinar useful? Yes. Could you please share your IDA files? Yes, all these files will be sent to you guys. So you will be able to see the predictive control. You'll be able to see what I did and all the other cases as well. Inspect them by yourself and see how they perform. Did you already connect IDA to Grasshopper? We have not. I don't know if some of our clients have. I don't see an issue. Well, I haven't used Grasshopper, to be honest. So
Neither have I. Could you please share your IDA file too? Yeah, the
yes,
examples will
yes. I said all these examples will be sent out. Interesting, but interesting. You're welcome, guys. You've been awesome. I think we are, we have still 100 left over time. We were really afraid this 90-minute format will be too long, but you guys were awesome. You stuck in there. The results are coming in. Let me close and share with you guys. This is what you voted. Help me figure out the purpose in life. That's 52%. I don't know if I should feel, sad or happy about this. And interesting, but I understand. Okay. Then let me ask you if you guys would like to have more topics concerned control. Should we do more of this? Or because the next topic will be boreholes, given by Sven and Jörgen, sizing, etc. It's a very interesting webinar. I think it will be given on week 17. But let us know if you would like to know more advanced level controls. What's the, explaining the differences between different control modules. That will help us design future webinars, because we plan on doing a lot of those in the future. And a slow rate, but we want to help out and have some material out there that helps our clients. Okay.
Are you going to turn this webinar into a video which could be watched again? The answer is yes.
Yes. It'll be a video, so we will immortalize our mistakes on video. So some results. Thank you for this feedback. 48% say yes, and 47% says sure. Why not? We have 5%. Okay, thank God nobody says I will actively protest if this ever happens. I was afraid of that. Okay, great. But then we could conclude this webinar. If you guys are happy, satisfied, you don't have any more questions, then that'll be great. In manual for control elements, the help in IDA file, I think inside IDA is pretty nice, and not a lot of users use that. It taught me a lot, the differences between the controls. And Per Carling, you have some courses as well, advanced level courses.
Yeah, we're giving courses on a regular basis. Actually, I think 4 times a year in different countries. Sweden, Finland, Germany, Switzerland. And so keep your eyes open and look at our website, and you will see when those occur.
Oh.
Yeah.
Okay. Then let's end this. Thank you guys again for joining. It was a real pleasure. Hope to see you next time. Bye-bye.
Bye-bye.